Welcome to The Explainer. Today we're diving into the fundamental concepts that power literally everything, from a lightning strike all the way down to your smartphone. We're going to explore the invisible landscape of energy that's all around us.
Okay, let's just jump right in with this incredible image. A lightning bolt just tearing across the sky. We see the flash, we hear that rumble of thunder, but what's really going on there? What's the engine behind that mind-blowing release of energy? Well, the answer isn't just about how much charge is built up in the clouds. It's really about the incredible potential for that charge to move, that gap between the cloud and the ground. And this idea, this concept of potential, that's the absolute core of what we're talking about today. To really get a handle on this, let's start with something we all kind of know from our day-to-day lives: gravity. You'll see the ideas are surprisingly similar, and it's a fantastic way to build up our understanding from the ground up. So, think about a ball sitting at the top of a hill. It has potential energy, right? That's based on its mass and how high up it is. While electric potential energy is pretty much the same exact idea, but instead of mass and height, we're talking about an electric charge and its position inside an electric field. We're essentially creating this invisible landscape of hills and valleys, but for charges. So moving between two different spots on this landscape, like climbing that hill, that takes work. It takes energy. The amount of work you have to do for each little bit of charge, well, that's what we call potential difference. And you already know this by a much more common name: voltage. It's the voltage you see on a battery. Okay, so if potential difference is the energy it takes to move between 2 points, what about the potential at just a single point? For that, we need a starting line, a universal reference point. In physics, we just decide that's a point infinitely far away, where there's basically no field. So the electric potential at any one spot is the work it would take to bring a charge all the way from that flat plane at infinity to that specific point on our landscape. And that brings us right to the volt. When a battery says it's, say, 9 volts, what it's really telling you is that it provides 9 joules of energy for every single coulomb of charge it moves from one end to the other. It's a measure of energy per charge. All right, so we've got the concept, the why. Now let's get into the how. How can we actually map this invisible landscape and start predicting how things are going to behave? And believe it or not, our mapmaker is this beautifully simple formula. It's what lets us calculate the electrical height, the potential, at any distance r away from a single source charge q. With this one little equation, we can map out the entire landscape it creates. Let's just quickly unpack this. Each part plays a really clear role. Q, the source charge, that's our hill maker. A bigger charge makes a steeper electrical hill. And just like you'd expect, as r, your distance, gets bigger, the height of that hill, the potential, drops off. And this, right here, is an absolute game changer. Unlike electric forces or fields, which are vectors, they have directions you have to worry about and do complicated math for, potential is just a number. It's a scalar. So if you have a bunch of charges creating a really complex landscape, you just calculate the potential from each one and add them up. Simple arithmetic. It makes analyzing complicated systems so much easier. Okay, so if electric potential is creating this invisible landscape, there's got to be a way to visualize it, right? To draw a map? And that is exactly where equal potential surfaces come in. They are basically the contour lines on our electrical map. Think about walking along the side of a mountain, perfectly level, so you're not going up or down. You're tracing a contour line on a topographic map. That's an equipotential surface. For a charge, moving anywhere along that surface takes zero work because its electrical height isn't changing at all. And these surfaces, they have some really cool properties that give us a powerful way to visualize what's going on. They tell us that the electric field, that's the force a charge would feel, is always strongest where these contour lines are packed closest together, and that force always points straight downhill, perfectly perpendicular to the lines. So, why? Why does all this theory about invisible landscapes and contour lines actually matter? Well, because understanding it is what allows us to engineer and build one of the most essential components in all of electronics: the capacitor. A capacitor is, at its heart, an energy reservoir. We're not just dealing with the random landscape nature gives us, we are deliberately engineering a very steep electrical hill in a very tiny compact space, so we can store energy and use it whenever we want. So this process right here, it shows us exactly how we turn that abstract idea of potential into real,
tangible, stored energy. A battery does the work of pulling charge from one plate and shoving it onto the other, building up that potential difference. And the energy the battery used to do that work, it's now stored right there in the electric field between those two plates.
And how good a capacitor is at its job is measured by its capacitance. This simple little ratio, C equals Q over V, tells us everything. It tells us how much charge, Q, a capacitor can store for a given potential difference, or voltage, V. The higher the capacitance, the better the reservoir.
Now, a single capacitor is useful, for sure, but the real power comes when we start combining them. Just like you can with resistors, we can hook up capacitors in different ways to get the exact energy storage properties we need for any circuit we're building.
Now, here's something you gotta watch out for, especially if you've already studied resistors. The rules for combining capacitors are kind of flipped on their head. When you put them in parallel, you just add their capacitances up to get a bigger total. But when you put them in series, you have to add the reciprocals, which actually gives you a smaller total capacitance. It's a little counterintuitive at first.
And here it is, the payoff. This formula tells us exactly how much energy we've managed to pack into our reservoir. And I want you to notice that V squared term. That's a really big deal. It means the stored energy grows like crazy with the voltage. If you double the voltage across a capacitor, you actually quadruple the energy it stores. So really, it all comes back to this one central idea. Understanding the why, this invisible energy landscape all around us, is what lets us engineer the how. We build capacitors, these carefully designed little energy reservoirs, to harness that potential so we can store and release energy to power our entire modern world. But here's the really wild part. The energy isn't stored in the metal plates of the capacitor. It's stored in the electric field that fills the space between them. And that leaves us with a pretty fascinating thought to chew on. If an electric field itself can hold energy, what does that imply about the true nature of what we call empty space? We'll let you ponder that one until our next explainer.